Hi class, how are you today? That's central to the limit. Um, I give up. Let's just move on. The learning target for today is to be able to calculate probabilities of an X-bar distribution from an X distribution. Your scale, a 3, you can calculate probabilities of an X-bar distribution from an X distribution. 2, you can find the area under any normal curve. 1, you can convert raw scores to z-scores and vice versa. And 0, you cannot convert raw scores to z-scores and vice versa. Let's get started. Section 6.5, the Central Limit Theorem. Focus points for this lesson. For a normal distribution, you use mu and sigma to construct the theoretical sampling distribution for the statistic x bar. For large samples, use sample estimates to construct a good approximate sampling distribution for the statistic x bar. Learn the statement and underlying meaning of the central limit theorem well enough to explain it to a friend who is intelligent but unfortunately doesn't know much about statistics. The x bar distribution given x is normal. In section 6.4, we began a study of the distribution of x bar values, where x bar was the sample mean length of 5 trout caught by children at the Pinedale Children's Fishing Pond. Let's consider this example again in the light of a very important theorem of mathematical statistics. Suppose a team of biologists has been studying the Pinedale Children's Fishing Pond. Let x represent the length of a single trout taken at random from the pond. The group of biologists has determined that x has a normal distribution with mean mu is 10.2 inches and standard deviation sigma is 1.4 inches. What is the probability that a single trout taken at random from the pond is between 8 and 12 inches long? Use the methods of 6.3 with mu is 10.2 and sigma is 1.4 to get z equals x minus mu over sigma, so x minus 10.2 over 1.4. Therefore, the probability that x is between 8 and 12 is the probability that z is between, and you plug stuff into the formula, you get negative 1.57 and 1.29, which will give you 0.9015 minus 0.0582, so 0.8433. Therefore, the probability is about 0.8433 that a single trout taken at random is between 8 and 12 inches long. To find the probability using a graphing calculator, instead of a table, you do second vars, which is the distra button, to normal CDF. Lower limit, upper limit, mean, standard deviation. So you press 2 vars, or second vars, normal CDF, 8, 12, 10.2, 1.4. 8 being the lower limit, 12 being the upper limit, 10.2 being the mean, 1.4 being the standard deviation. And that'll give you 0.8427. This is slightly different than the previous calculation, but not significantly. The previous calculation was 0.8433, just 0.0006 difference. What is the probability that the mean x bar length of 5 trout taken at random is between 8 and 12 inches? If we let mu of x bar, that's the mean of x bar, represent the mean of the distribution, then Theorem 6.1 Part B tells us that the mean of x bar is the mean, which is 10.2. If sigma x bar represents the standard deviation of the sigma x bar distribution, then Theorem 6.1 Part C tells us that sigma x bar is equal to sigma divided by the square root of n, which is 1.4 divided by the square root of 5, which is about 0.63. To create a standard z variable from x bar, we subtract mu sub x bar and divide by sigma sub x bar. And we get z equals x minus mu sub x bar divided by sigma sub x bar, which is pretty much what we've been dealing with, just replacing x with x bar. So that gives us x bar minus mu over sigma divided by the square root of n. So x bar minus 10.2 divided by 0.63. To standardize the interval 8, our x bar is between 8 and 12. We use 8 and then 12 in place of x bar in the preceding formula for z, and we get that z is between negative 3.49 and 2.86. Theorem 6.1, part A, tells us that x bar has a normal distribution. Therefore, the probability that x bar is between 8 and 12 is the probability that z is between negative 3.49 and 2.86. So that gives us 0.9979 minus 0.0002 to give us 0.9977. So the probability is about 0.9977 that the mean length based on a sample size of 5 is between 8 and 12 inches. Using a graphing calculator, again you do second var's normal CDF, lower limit which is 8, upper limit which is 12, mu which is 10.2, and sigma divided by the square root of n, which is 1.4 divided by the square root of 5. Made sure to put that in there just like it is. And that gives us 0.9978, which is just a little off from 0.9977, just 0.0001 difference. Looking at the results of parts A and B, we see that the probabilities 0.8433 and 0.9977 are quite different. Why is this the case? According to Theorem 6.1, both x and x bar have a normal distribution, and both have the same mean of 10.2 inches. The difference is in the standard deviations for x and x bar. The standard deviation of the x distribution is 1.4. The standard deviation of the x bar distribution is 1.4 divided by the square root of 5, which gives us about 0.63. The standard deviation of the x bar distribution is less than half the standard deviation of the x distribution. So we have these two graphs. The first is the x distribution with a much larger standard deviation, so it's much more spread out. The second is the x bar distribution, much smaller standard deviation, so it's much more skinnier. Looking at those figures, we see that both curves use the same scale on the horizontal axis. The means are the same, and the shaded area is above the interval from 8 to 12 on each graph. It becomes clear that the smaller standard deviation of the x-bar distribution has the effect of gathering together much more of the total probability into the region over its mean. Therefore, the region from 8 to 12 has a much higher probability for the x-bar distribution. The standard error is the standard deviation of a sampling distribution. For the x-bar sampling distribution, the standard error is sigma divided by the square root of n. The x-bar distribution given x follows any distribution. Using the central limit theorem to convert the x-bar distribution to the standard normal distribution, mu is mu, so the mean of the x-bar distribution is mu. Sigma is sigma divided by the square root of n, so the standard deviation of x-bar is sigma divided by the square root of n, and then z is x-bar minus mu sub x-bar divided by sigma sub x-bar. Again, what we've been dealing with for the last few sections. Where n is the sample size, greater than or equal to 30, mu is the mean of the x distribution, and sigma is the standard deviation of the x distribution. So this is saying that it works for any distribution, not just normal distributions, as long as n is greater than or equal to 30. A certain strain of bacteria occurs in all raw milk. Let X be milliliter of milk. The health department has found that if the milk is not contaminated, then X has a distribution that is more or less mound-shaped and symmetrical. The mean of the X distribution is 2,500 and the standard deviation is 300. In a large commercial dairy, the health inspector takes 42 random samples of the milk produced each day. At the end of the day, the bacteria count in each of the 42 samples is averaged to obtain the sample mean bacteria count X bar. Assuming the milk is not contaminated, what is the distribution of X bar? The sample size is 42. Since the value exceeds 30, the central limit theorem applies, and we know that X bar will be approximately normal, with mean and standard deviation of 2,500 for the mean and standard deviation of 300 divided by the square root of 42, which is 46.3. Assuming the milk is not contaminated, what is the probability that the average bacteria count X bar for one day is between 2,350 and 2,650 bacteria per milliliter? We convert the interval to a corresponding interval on the standard z-axis. So we get 2,350 converting to negative 3.24 and 2,650 converting to 3.24. So the probability that X bar is between those two numbers is that the probability that z is between negative 3.24 and 3.24. So we get 0.9994 minus 0.0006, and we get 0.9988. The probability is 0.9988 that X bar is between those two numbers, 2,350 and 2,650. Using your graphing calculator, second vars, normal CDF, 2,350, lower limit, 2,650, upper limit, 2,500, the mean, and 300 divided by the square root of 42, the standard deviation, which gives us 0.9988, which is the same as what we had here. At the end of each day, the inspector must decide to accept or reject the accumulated milk that has been in cold storage waiting shipment. Suppose the 42 samples taken by the inspector have a mean bacteria count X bar that is not between 2,350 and 2,650, so either below 2,350 or above 2,650. If you were the inspector, what would be your comment on this situation? The probability that X bar is between 2,350 and 2,650 for the milk that is not contaminated is very high, specifically 0.9988. So 99.88%. It's pretty high. If the inspector finds that the average bacteria count for the 42 samples is not between 2,350 and 2,650, then it is reasonable to conclude that there is something wrong with the milk. If X bar is less than 2,350, you might suspect someone added chemicals to the milk to artificially reduce the bacteria count. If X bar is above 2,650, you might suspect some other kind of biologic contamination, which is a really bad thing. You don't want a lot of bacteria in your milk. How to find probabilities regarding X bar. Given a probability distribution of X values, where n is the sample size, mu is the mean of the X distribution, and sigma is the standard deviation of the X distribution. 1. If the X distribution is normal, then the X bar distribution is normal. Number 2. Even if the X distribution is not normal, as long as the sample size is greater than or equal to 30, then by the central limit theorem, the X bar distribution is approximately normal. Number 3, convert X bar to Z using the formula we've been using. And number 4, use the standard normal distribution to find the corresponding probabilities of events regarding X bar. Now time for the sponge. The heights of 18-year-old men are approximately normally distributed with a mean of 68 inches and a standard deviation of 3 inches. If a random sample of 9 18-year-old men is selected, A. What is the mean of the X bar distribution? B, what is the standard deviation of the x-bar distribution? And C, what is the probability that the mean height x-bar is between 67 and 69 inches? Alright, that's it for the lesson. Once again, please make sure to take notes in the entire lesson. Take a picture of your notes. Go back to the beginning. Rate yourself. Submit it all to Google Classroom. And have a good night.